Yes, and so would you believe it? We now come to the definition of OR. Right, we begin by filling out the inputs of our table. Remember, find the rightmost one, in this case B, and start with 0. So false, true, 0, 1, 0, 1. And because we have two inputs, 2 times 2 is 4, we therefore need 4 rows on our table. Moving from right to left, we double the pattern up, so 0, 0, 1, and that gives me all possible inputs. Again, we have light bulb A, light bulb B, and the statement for this column being true or false is bulb A is on. Statement for this column is bulb B is on, and we're now going to investigate, is A or B on. So the statement is A or B is on. Right, looking at it from the perspective through the OR goggles. Before we get to that, let's look at the shape of the OR gate as a logical symbol. It has a rounded tail and a very pointy nose. That's the shape for an OR gate. Right, moving on. Placing our situation 1, both bulbs are off. In other words, the statement bulb A is on is false, bulb B is on is false. Looking at it from this point of view, looking through my OR goggles, I'm answering the question, is bulb A on or bulb B on? That's either true or false. So the question, well, rather more to the point, the question is A or B is on is actually false, because they're not. That's not true. A or B is not on. Right, we now move on to permutation number 2. Bulb A has remained off. Bulb B is now on. Looking at it through the perspective of my OR goggles. A or B is on. It's true, because B is on. One of them is on. A or B is on. Or means is one of them. And, remember, means is both of them. Right, looking at permutation A being on, B being off. Can I answer the question? Is A or B on? And the answer is, it's true, because A is on. So one or the other is on. It's true, because A is in fact on. Moving now into our final permutation, where both A and B are on. Is A or B on? Well, A is on. Is B on? Yeah. So either A or B is on. It doesn't matter that they're both on. It's still true that either one or the other of them is in fact on. So, we arrive at the following definition for an OR. You can see that we have a short circuit definition yet again. Whenever any one of the inputs or both of the inputs were in fact a 1, we can now automatically say the minute one of the inputs is true or 1, I automatically can then say that the output has to be a 1. The only time we do not get a 1 out is when all the inputs are in fact false. And those are the conditions that need to be checked more carefully. So the short circuit definition for an OR is if you find a 1 anywhere, you automatically can say you're getting a 1 back out. That is the OR.